I wanted to work through an example of the right-hand rule. This is the rule that tells us or reminds us the direction of the magnetic force on a moving charged particle in a magnetic field. So it's the relationship. It encodes the relationship between the direction of the force, direction of the motion, and the direction of the field, the three directions in the magnetic field equation. So in this question, there are 6 pictures of a moving charged particle in a magnetic field. And they tell us the orientation of the charged particle, its motion, and the orientation of the magnetic field. And we're going to figure out the direction of the magnetic force with right-hand rule. I'm going to go through and do it once, assuming the moving charged particle is a positive particle. So I'm going to denote in this color here my answers for a positive particle. And then we'll do the same thing for a negative particle. See what the differences are. Okay, so let's start with A. In A, the velocity of the moving charged particle is indicated by the red arrow, it's up. The magnetic field is indicated in green with these crosses, that's into the screen. So I'm going to use the right-hand rule to take those two directions, the direction of the velocity vector, the direction of the magnetic field, to figure the direction of the force on that moving charged particle. So I'm going to take my right hand. I'm going to point the palm of my right hand in the direction of the velocity vector, that's up. I'm going to curl my fingers of my right hand in the direction of the magnetic field, that's into the screen. My thumb will point in the direction of the magnetic force on a positive moving charged particle. So that's over on the left. The force on the particle, positive charged particle, is towards the left. Let's go on to B. So in B, the velocity of the moving charged particle is up again. So the palm of my hand is going to point up. The magnetic field is now changed, is towards the right. So I'm going to curl my fingers towards the right. And my thumb then points in towards the screen. And so the force on a positive moving charged particle is in towards the screen. I'll denote that as this solid dot. On to C. I'm going to get faster and faster as I walk through these. On to C, I've got the velocity vector pointing towards the left-hand side. I've got a magnetic field that's pointing downwards, so I'm going to curl my fingers downwards. And that tells me, through the direction of my thumb, which is pointing out of the screen, that the magnetic force on this positive moving charged particle is out of the screen. So I'm indicating that with a solid dot again. On to D. On D, we've got a velocity vector that is again from the right to the left. So palm of my hand, again from the right to the left. I've got a magnetic field this time that is indicated by dots. That means out of the screen. So I'm curling my fingers out of the screen. And my thumb is pointing upwards on the screen. So the force on a positively charged moving charged particle is upwards in this case. E and F. Now maybe these look a little scary because it's not right angles between the directions of the velocity vector and the magnetic field vector. But still, the right-hand rule applies. Still, you point the palm of your hand in the direction of the velocity vector, and then curl your fingers towards the magnetic field direction. Okay, so let's do E. I'm going to point my palm of my hand in the direction of the velocity vector. So that's partially upwards and partially towards the right. I'm then going to curl my fingers towards the direction of the magnetic field. So that's making my fingers point just towards the right. And my thumb is pointing in towards the screen. So in this case, the magnetic force is into the screen. I'm indicating that with a cross. Okay, finally part F. So in this case, we got a velocity vector that is pointing to the left partially and downwards partially. So I'm going to point the palm of my hand to the left and partly downwards. And then I'm going to curl my fingers of my right hand in the direction of the magnetic field. So that magnetic field is pointing towards the right. So I'm curling my fingers over towards the right. My thumb is pointing out of the page. And so the magnetic force on a positive moving charge particle is out of the page. So those are the results that we've got for the right-hand rule with these 6 different configurations of velocity vectors, magnetic fields, and resulting magnetic forces. And let's just walk through the answers and see if a few things make sense to us. So one thing that's important is that the magnetic force is always at right angles to the magnetic field and the velocity vector. So there's 2 vectors that create the magnetic force, so the velocity vector and the magnetic field. They kind of define a plane. They live in a plane, and the force vector is always perpendicular to that plane. And so let's double check that that's true. In A, the velocity vector is up, the magnetic field vector is in, and the force vector is towards the left. So that is at right angles to both the velocity vector and the magnetic field. In B, the velocity vector is up, the magnetic field is towards the left, and the magnetic force vector is out of the page. Again, that's at right angles to the velocity vector and the magnetic field. In C, right, the velocity vector is towards the left, the magnetic field's down, and the magnetic force is out of the page. Again, it's at right angles to the 2 other vectors. And I'll just do one more here. The velocity vector's towards the left, the magnetic field's out of the page, and the force vector is upwards. Again, that's at right angles to the 2 other vectors, the B field and the velocity vector. And that's true downstairs here, right? The velocity vectors and the magnetic fields in the parts E and F are in the plane of the page, and the force vector is either out of or into the page. So the force vectors are perpendicular to the velocity vector, the magnetic field vector, the plane that's defined by the velocity vector and the magnetic field vector. What about a negative charge particle? Let's indicate the direction of the forces on a negative charge particle. So let's pick another color here. And we're going to denote the forces on a negative charge particle in orange. And here, since we worked out all the forces on a positive charge particle, indicating the forces on a negative charge particle is going to be simple and straightforward. I'm not going to go through and repeat the right-hand rule each time for A, B, C, D, and E, and F. I'm just going to say that whatever we figured the force on a positive charge particle, the force on a negative charge particle is in the opposite direction. And that comes about because, for a positive charge particle, Q is positive, plus. For a negative charge particle, Q is negative, minus. The plus and the minus means that the directions of those force vectors are opposite one another. The arrowhead on the force vector is moved from one end of the force vector to the other end of the force vector. So I'm just going to indicate the directions on a negative charge as opposite the positive charge. So in A, the force was towards the left on a positive charge, is towards the right on a negative charge. In B, the force was out of the page on a positive charge, is going to be into the page on a negative charge. In C, the force was out of the page on the positive charge, is going to be into the page on the negative charge. In D, the force was up on the positive charge, is going to be down on the negative charge. In E, the force was into the page on the positive charge, is going to be out of the page on the negative charge. And in F, the force was out of the page on the positive charge, is going to be into the page on the negative charge. And that's it, folks. That's the right-hand rule. That's 6 examples of the right-hand rule. Remember to use your right hand. That's the first part of the right-hand rule. Remember to use the plane of your palm as the direction of the velocity vector. That's important. It's the first vector in the field equation. And then curl your fingers in the direction of the magnetic field. That's the second vector in the magnetic field equation.